Okay, we will continue. So the next presentation is from Aurelien Lequertier, Edge Impulse. Go ahead.
Thank you. Good morning, everyone. Really glad to be here after 2 years not having any in-person conference. So my name is Aurelien, and I lead the solutions team at Edge Impulse. And today we're going to talk about 2 new innovative techniques that we've developed. The first one about keyword spotting. So if you imagine the OK Google or Alexa type of applications, how you can do that but by using only a few dozens of audio samples. And the second one would be around object detection and how we can run that on microcontrollers with very low latency. We have the clicker. Oh, yeah. I try, yeah. OK, sounds good. And so just a few words about Edge Impulse before diving into the technical topics. So Edge Impulse, we've developed a platform for embedded engineers, data engineers, and data scientists to simplify the deployment of embedded application on very small targets. So targets going from tiny microcontrollers up to CPU and GPU type of edge devices. And so using Edge Impulse, you can do everything that you can imagine in a machine learning pipeline, from data collection. So usually with data collection, you can do that either by importing your own data set. So if you imagine you want to do image recognition, you can import your image data set. If it's audio, you import your audio samples. If you want to do vibration analysis, you can import CSV or JSON files. But one cool feature that we have is we've also developed firmwares for all the edge devices we officially support on the platform. And so when you flash the Edge Impulse firmware on your target, you can directly connect your edge device to the Edge Impulse platform. So we've got a really nice CLI that helps to basically act as a proxy between your edge device and the web platform. And you can directly collect data from your edge device. So collecting images if you have a camera on the device, collecting audio samples, or collecting any type of data, if you have an accelerometer on it. So you collect data, and then the second step in any machine learning project is to design your neural network and everything around that. Because usually with machine learning, it's not only about neural network, but signal processing is super important. We're going to talk about that with the keyword spotting, but using signal processing is important to extract meaningful features. So it's something you can design directly using our UI. So designing signal processing blocks and then neural network blocks. And afterwards, you can, of course, test and train your model and check the performances directly on the platform. And in the end, you can deploy back the model, which includes both the signal processing and the neural network directly on your target. And for the deployment, you've got different options. If you use an edge device that is supported by the Edge Impulse platform, you can create a binary firmware for that. But we can also deploy a C++ library which has no specific dependencies that you can run on most microcontrollers as long as you have a C++ compiler. And so for instance, if you are running it on an ARM Cortex device, we will leverage CMSIS-NN, CMSIS DSP instructions to run it as fast as possible on this target. Just a few key figures about the platform. So the platform has been launched around 2 years ago. And so at the moment, we've got a bit more than 40,000 developers using Edge Impulse. So we actually really like developers communities. So we've got a free tier for Edge Impulse. So if you are interested in trying it out, you can just go to edgeimpulse.com and sign up and start building your own embedded machine learning projects. And then we've got also like enterprises features if you want to do more intense thing regarding computing, and if you need to do like some data pre-processing, for instance, which is usually super important when you are dealing with very big data sets. And so yeah, here are some of our customers that we are working with. Also, we work with a lot of silicon vendors, like the majority of silicon vendors, like ST, Microchip, Arduino, Raspberry, Nordic, are partners that we have and that are supported on the platform. And so I've already talked a bit about different use cases, but what's interesting with the platform, as I said, like we are able to deploy, create a C++ library that can run on any type of target. So going from ultra low power microcontrollers to like really high-end GPU, like NVIDIA Jetson Nano. And it's interesting because with this flexibility, you can run different type of use cases. If you want to do like vibration analysis, anomaly detection, you can do that on very tiny microcontrollers. And then if you want to do like audio, image, or video, it's something you can do as well if you are selecting an higher end microcontrollers. So let's look at the first technique we've developed about keyword spotting. That's called few-shot keyword spotting. So before explaining how we've developed the few shots, it's just a simple diagram to explain how keyword spotting works. So as with any machine learning project, like the first thing you need to do is to create a data set and collect data. So like if you want to recognize like the yes keyword that like you can see here on the slide, you're going to have to collect tens, hundreds, probably thousands of samples if you want to reach like really high accuracy. And the second step would be to do what we call like features extraction. Like you are not taking your data set and basically throwing the data directly to the neural network. Like you will get more meaningful features if you run first some signal processing on the target. And one of the features that's actually very useful for speech recognition is called MFCC. So that's an example of spectrogram you can see here. So that's very useful for speech recognition. And in the end, you will get the neural network, which is usually like a convolutional neural network for audio type of application. So here we've got like some examples of configuration for both the MFCC and the neural network, like the typical configuration we use for keyword spotting. So if you look at on the left side, so you've got like the configuration on MFCC where the idea is to split your frame in subframes. So like if you have like a frame of 1 second to detect your keyword, you're gonna split it in like subframe of like 20 milliseconds, and then different frequency steps as well to extract meaningful features. And then you're gonna have your convolutional network. So here's an example of neural network architecture that we use for keyword spotting. But one of the problems with keyword spotting is if you want to reach like really high accuracy and optimize like your false acceptance, false reject rate, you will need like to get a really big data set in the end. So like it's quite easy to get like a 70, 75% accuracy, but if you want to reach like 95, maybe 99% accuracy, you're gonna need like pretty big data set. And so it's really time consuming creating a data set for that. So here's just some example of models that has been trained for keyword spotting, where you can see like with around like 500 audio samples, you've got 75% accuracy for this particular use case. And on this one, you've got like 87% accuracy, which is actually pretty good. But for this particular one, you can see like we've got roughly like 10,000 samples. So you need like a lot of friends to basically like help you out to create the data set. And so the solution we can come with regarding keyword spotting and the few-shot keyword spotting is, if we look at like image classification and how it's done right now, we've got a technique called transfer learning. And it's exactly what we are reusing in order to train keyword spotting model faster with just a couple of samples. So like if we look at a usual image classification model, like this one, like on the top, which, like you can imagine, like the mobile net type of network that has been pre-trained on the image net. So the image net is like a huge data set of millions of images of like dogs, cats, the usual things you want to detect on the internet. And so you pre-train this mobile net network with lots of images, and then you use this transfer learning technique where basically the idea is just to fine-tune the last layers of the neural network with the specific images that you wish to classify. So here's just some example where you're trying to detect some serious cells using transfer learning techniques. And so if we do the same thing with audio, like the difference, it's basically that we are going to replace the images by the audio spectrogram instead. And so like the models that we have trained, so it's also based on the mobile net network, but it's been trained of like 25 million of keywords in different languages in order to get this first model, in order to get few-shot keyword spotting working. So once we've trained this model, we can apply the regular transfer learning technique as well and be able to get like very high accuracy with just a couple of samples. So here in these examples, we've got a model we've trained to recognize a couple of keywords like OK edge, green light, red light. And the model has been trained with around 20 audio samples for each of the keywords we wish to detect. And we reach like a 97% accuracy, which is like super high compared to what you would do with regular keyword spotting application. And I'm going to show you like a quick demo from my coworker, if the link works. I would just play it a bit faster. So as I was saying, like if you're interested to try Edge Impulse, you can go on the website and directly create an account. Or if you want to try this few-shot keyword spotting, you can just go on the website. There is an evaluate link. You don't even need to create an account. And then it's guiding you through how to create this model. So here, like my coworker wants to detect the Hello Louis keyword. And so you just use your laptop to record a couple of like audio samples, so like repeating Hello Louis 20, 25 times. So using this wizard is like super easy to get started. And once you've finished training your model, you can like create your free account if you wish, for instance, to deploy it on a specific device. So here this step is basically like on top of like adding keywords that you wish to detect, you also want to add like additional data that is not the keyword that you are interested in. So like some noise, or like random keywords in order to increase the robustness of the neural network. And so then the next step is here, like configuring the spectrogram using like default parameters. Usually, like is enough to get like the expected performances. And so once you finish generating keywords, we've got like this dimension reduction algorithm that we use to look like on the 3D view, like if basically the different audio samples are separated or not. So it's like really nice to see, for instance, if you did like some like false labeling, which happens quite a lot when you have like big data sets. And here like the next step is basically like training our model. So here you can see the models that is used is like a MobileNet V1, but we've got both MobileNet V1 and V2, depending on the target you have, if you have like how much RAM and flash you have on your device. And in the end here, you've got like the accuracy of your model. So like super easy, like you can do that basically like in 5 minutes. It's being done now, it's like the project is being built. So like all the inferencing engine is being put inside like a WebAssembly package. So we can run it directly on the laptop and you don't need even to deploy it on a device. And you can see live like the classification of the model. And you see like the peak RAM usage, flash usage as well for this. So like super easy, like in just 5 minutes, if you want to build your own keyword spotting, you can start doing that. And what we don't show here in the video is at the end, you can also decide to deploy it to directly an edge device. So like if you have a Portenta and ST discovery kit, you can just select it and you will get like a binary firmware with your model running directly on the target. So going through the second technique we want to talk about, which is that we call FOMO, faster objects, more objects, which is also based like on the transfer learning technique. So in general, when we talk about computer vision, it's being classified into two types. So the first one being like regular image classification, where you have an image and you want to say like, okay, is this image like a plant here? Or is this a lamp or a person? So like regular image classification model. And the second one is object detection. And so like for object detection, the idea is to be able to detect like multiple objects, people, animals, and also like having the exact location in the image. So they are like the two usual type of computer visions techniques. But one of the issues is like when you want to run that object detection on microcontrollers, it's actually really hard because to run object detection, you need like pretty big models. So like if you are, for instance, thinking of like YOLO or single shot detectors, it's very accurate, it works really well, but they are really big and computer intensive. So it's not something that you can usually run directly on microcontrollers. So for instance, like one part that is like very power hungry for object detection is finding bounding boxes. So you're gonna create like hundreds, sometimes thousands of bounding boxes in order to see like, oh, do you have a dog? Do you have the bike here in the picture? And this is very, very intensive. And after that, you're gonna have a last algorithm called non-maximum suppression where the algorithm will try to find the best bounding box for the different objects in the pictures. And this, yeah, takes a lot of power. And so without going too much into all the details here, but the part that is like very power hungry here, this is like a MobileNet SSD object detection model. Like you've got like the last layers, like the extra features layers that are used to create those bounding boxes. And like for instance, in this model, you will get like thousands basically of bounding boxes per class that you wish to detect. And that's the part that's very power intensive for object detection. And so how do we get something that can run on microcontrollers? So the idea that our machine learning team had was to look a bit more closer to regular image classifications transfer learning models. So I was mentioning a bit earlier about keyword spotting, like for image classification, that we use like a MobileNet network to be able to pre-train and then fine-tune your model. So if we look a bit deeper into that and how it works, so this is basically like a representation of an image classification neural network. And how it works is you're going to have like different convolutional layers that are going to look at different features in the pictures. So finding different features in those pictures, and then at the end, you've got like additional like connected layers that are basically making the link between those feature maps and the images that you've trained in order to get some prediction in the end. So having prediction saying like here, our image is like probably a tree with 90% accuracy. But if we look a bit closer to this part, like basically like the feature maps, it gives you like a representation of what's inside the pictures like at different locations. And that's the idea we use for our constrained object detection. So we're gonna check like a different location in the image, like does it contain the object that we are looking for? And so basically taking like for instance this MobileNet network, but replacing the last fully connected layers with what we call this per region class probability map. And in the end, what we get is a model which is actually doing object detection, but using a model that's actually more optimized than regular image classification. And so much better than regular object detections because you don't have to deal with like the bounding boxes and non-maximum suppression algorithm. And so here on the right side, you've got some example of like different type of screws that are detected using the FOMO algorithm. As I was saying, it's based on the MobileNet architecture. And what's interesting is that it's actually like really fast. So if you look here at the couple of numbers we have, like on a Raspberry Pi, you can get up to like 60 frames per second. If we compare to like a regular object detection using like MobileNet SSD on the Raspberry Pi, we would get like 3 frames per second. So it's like 20 times faster. And the model is also like 30 to 40 times smaller compared to the regular MobileNet SSD. But what's actually even more interesting is like we can run that on microcontrollers. So like on Cortex M7, you can get 30 frames per second, and on the Cortex M4, you can get up to 10 frames per second. And so we've got like different type of models, different type of MobileNet networks that you can use for different type of image resolution, but typically like the smaller model we have running on the Cortex M4 using like grayscale images and 100 by 100 pixel images, it's taking less than 100 kilobytes of RAM to run on the target. And the model is also like much better at detecting smaller and a lot of objects in a picture compared to regular object detection. So it's just a last slide about, I mean, how it works for training and also like detecting objects. So we create like those heat maps for object locations to know like exactly where the objects are located. And this heat map can be like configurable. So if I give you like an example, like if we have an image with 160 by 160 pixel, by default, we create a heat map which is 8 times smaller, which will be like basically like 20 by 20, a matrix of 20 by 20. And it means that we can theoretically detect up to 20 times 20 objects, which yield to 400 objects. But you can even have like pixel precision if you want to. Like if you have a heat map which is the same size of your image data set, you could detect like very, very tiny objects. Yeah, and the last thing is we train object on centroid, so we still use like bounding boxes to label the data, label the objects in our data set, but the training is done like on centroids of the objects, because we don't usually like you don't you don't really care about the size of object that you detect. What is important to you is how many objects do I have in my image and what is the location of those. And so last quick video on detecting bottles of beer. So that's our CTO, Jan, who did this video a couple of days ago, so you can see like cans of Coke and beer bottles being detected. So this is running on a Arduino Nicla board, so it's Cortex M7. This one is running at like 30 frames per second. Yeah, so as I say, like if you're interested to try out Edge Impulse, just go on the website and click on Get Started, and you can create your free account. If you're interested in trying the few-shot keyword spotting, you can even do so without creating your account if you go to this link, studio.edgeimpulse.com/evaluate. If you want to know more about FOMO or Edge Impulse in general and all the features, we've got like 2 links here related to FOMO and the documentation. Thank you.
Okay, thank you. Do we have questions? I have one question related to this audio recording. Let's say that I would like to have a tiny machine learning solution on my microcontroller and I have a certain microphone in there. But if I collect my audio data by using, let's say, mobile phone, it's a different microphone. How big is this problem in the inference time?
Yeah, that's a good question. So what we do, like when you create your Edge Impulse project and you create your audio data set, is so like we auto-detect like the sampling frequency. So like the sampling frequency would be like the important thing, like if you have that different microphones. And so we can do like directly like downsampling inside your Edge Impulse project. So for instance, if you collect data with your smartphone and it's like 44 kilohertz sampling frequency, you can select downsampling to 16K, and then what you will get on your board will also be something that will be downsampled to 16K.
How about the microphone? Like the microphone capabilities may be a bit different. Does it make any difference in the inferencing then?
Yeah, like the gain typically will be like important. So like if you collect data and you've got like microphones with different gains. And so in this case, what you will need to do so is like when you deploy the C++ library that we have, like for most of the boards, you've got parameters to tune the gain directly on the board. And so it's something that would usually like be a good thing to do if you want to get like similar, like good performances and basically like match the microphones that you use for data collection and the one you use on the target for inferencing.
Okay. More questions?
Hey, sorry, I missed the initial part of the talk, but could you maybe elaborate on, so when you're doing keyword spotting and you pick an arbitrary keyword, you can probably only record like a 10, 20, 30, 40 samples, which in relation to the entire data set is a very small number. So how do you still make sure that, you know, it's still robust?
Yeah, so I can just go back quickly to this slide, and probably that's the part you've missed. So yeah, so we use like basically like a transfer learning technique for few-shot keyword spotting. So like the same transfer learning technique you have for image classification, but the idea is like we've trained the model on like 20, 25 millions of keywords in multiple languages, and then we use a similar like transfer learning technique using MobileNet. And so by doing that, we can get very good accuracy with just a few samples. So like this example where we have like 20 occurrences and having high accuracy.
Thanks.
What is the image resolution in the object detection you used?
So it really depends on the target, because the higher the resolution is, like the more power you would need as well. But you can use like 320 by 320 pixels, 160 down to 96 or even 48 pixels images to run the target.
Okay.
Thanks for the talk. Are your model open source or closed source?
Yeah, that's a good question. So the C++ library that we generate is fully open source. And so like there is no royalties on the code that's generated by the platform. And our SDK is also fully open source with Apache. So if you go on our GitHub, we've got lots of different repositories that are available. The only thing that's not open source is like the web platform that we have. And also we've got our own compiler to compile, to go basically like from the TF-Lite model to a C++ library. And this part is not something that is open source yet, at least.
Okay, but the models, like the detection models, we can find the information on your GitHub?
Yeah, and actually when you use a platform, so I don't know if it was in one of the slides, but like what you have here on the right side, it's an example of a neural network that you can reconfigure using the Edge Impulse platform, but you also have an option to use Keras directly, and so you can switch to Keras and fine-tune your model or even import your own model to the platform.
Okay, great. And last question, do you have any benchmark with like TensorFlow Lite? Did you compare the performance of your inference engine with TensorFlow and other inference engines?
Yeah, we've got something in our documentation. If you're looking for performances, you should find something about metrics.
Okay, thanks.